Welcome. Today we're diving into the fascinating world of chemical equilibrium. Have you ever wondered why some reactions seem to stop before all the reactants are used up? That's where equilibrium comes in. In chemistry, equilibrium is a state where the forward and reverse reactions occur at the same rate, so the concentrations of reactants and products remain constant over time. It's not that the reaction has stopped, but rather that it's reached a balance. This concept is crucial for understanding many processes from industrial production to biological systems. Let's explore what equilibrium really means and why it's so important in chemistry. Chemical equilibrium is dynamic, not static. This means that even though the concentrations of reactants and products stay the same, the molecules are constantly reacting with each other. The forward reaction, where reactants turn into products, and the reverse reaction, where products revert to reactants, happen at the same rate. Imagine a busy street where cars move in both directions equally. There's constant movement, but the number of cars on each side stays the same. This dynamic balance is what makes equilibrium so interesting and essential for many chemical processes. Not all chemical reactions are reversible, but equilibrium only applies to those that are. In a reversible reaction, products can change back into reactants under the right conditions. This is shown with a double arrow in chemical equations. For example, the reaction between nitrogen and hydrogen to form ammonia is reversible. Understanding which reactions can reach equilibrium helps chemists control processes and yields. Reversible reactions are at the heart of equilibrium, allowing systems to adjust and maintain balance. Equilibrium constant, often represented as K, is a number that expresses the ratio of product concentrations to reactant concentrations at equilibrium. Each reaction has its own unique K value, which depends on temperature. A large K means products are favored, while a small k means reactants are favored. This constant helps chemists predict the outcome of reactions and how changing conditions might affect the balance. Understanding K is key to mastering equilibrium. Calculate the equilibrium constant. We use the equilibrium expression. This is written as the concentration of products raised to their coefficients, divided by the concentration of reactants raised to theirs. For example, for the reaction plus BBCC plus DD, the equilibrium expression is K equals CCDD AABB. This formula allows chemists to plug in values and determine the position of equilibrium. It's a powerful tool for analyzing chemical systems. Equilibrium can occur in systems where all reactants and products are in the same phase, called homogeneous equilibrium, or in different phases, known as heterogeneous equilibrium. For example, a gas phase reaction is homogeneous, while a reaction involving solids and gases is heterogeneous. The distinction is important because solids and pure liquids are not included in the equilibrium expression. Recognizing the type of equilibrium helps in setting up the correct calculation. Chatelier's principle states that if a system at equilibrium is disturbed, it will adjust itself to counteract the disturbance and restore equilibrium. This means that changes in concentration, temperature, or pressure can shift the position of equilibrium. For example, adding more reactant will push the reaction toward producing more product. This principle is widely used in industry to optimize chemical yields and control processes. When the concentration of a reactant or product is changed, the system responds to minimize that change. If you add more reactant, the reaction shifts toward the products. If you remove a product, the system also shifts to produce more product. This response helps maintain balance and is a direct application of Le Chatelier's principle. Understanding this effect is crucial for controlling chemical reactions in the lab and in industry. Temperature changes can also shift the equilibrium position. If the reaction is exothermic, increasing the temperature shifts equilibrium toward the reactants. If it's endothermic, raising the temperature favors the products. This is because the system tries to absorb or release heat to counteract the change. Temperature control is vital in industrial processes to maximize yields and efficiency. Pressure changes mainly affect reactions involving gases. If you increase the pressure, the equilibrium shifts toward the side with fewer gas molecules. Decreasing the pressure shifts it toward the side with more gas molecules. This is another way to control the outcome of a reaction, especially in industrial settings like the synthesis of ammonia. Understanding pressure effects is key for optimizing gas phase reaction. Catalysts speed up both the forward and reverse reactions equally, helping the system reach equilibrium faster. However, they do not change the position of equilibrium or the value of the equilibrium constant. Catalysts are essential in many industrial processes, making reactions more efficient without altering the final balance. Their role is to provide a quicker path to equilibrium, not to shift it. One of the most famous examples of chemical equilibrium is the Haber process, used to synthesize ammonia from nitrogen and hydrogen. This reaction is reversible and reaches equilibrium under specific conditions of temperature and pressure. By manipulating these conditions, chemists can maximize ammonia production, which is vital for fertilizers and agriculture. The Haber process showcases how equilibrium concepts are applied in real-world industry. Equilibrium isn't just important in industrial chemistry, it's also vital in living organisms. Many biological processes, such as oxygen transport in blood, rely on equilibrium reactions. Hemoglobin binds to oxygen in the lungs and releases it in tissues, all governed by equilibrium principles. Understanding these balances helps explain how our bodies function and adapt to changes in the environment. Solubility equilibrium occurs when a solid dissolves in a liquid, and the rate of dissolving equals the rate of precipitation. This balance determines how much of a substance can dissolve in a solvent at a given temperature. Solubility products, or Ksp values, help chemists predict whether a precipitate will form in a solution. This concept is crucial in fields like environmental science and medicine. Acid-base reactions also reach equilibrium. The strength of an acid or base depends on how much it dissociates in water. Weak acids and bases only partially dissociate, establishing an equilibrium between the undissociated and dissociated forms. The equilibrium constant for acids is called Ka, and for bases Kb. These values help chemists understand the behavior of acids and bases in different environments. Buffer solutions are mixtures that resist changes in pH when small amounts of acid or base are added. They work by establishing an equilibrium between a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffers are essential in biological systems, laboratories, and industry to maintain stable conditions. Understanding buffer equilibrium is key for many scientific applications. Common ion effect occurs when a compound containing an ion already present in the solution is added. This shifts the equilibrium, usually decreasing the solubility of a salt. For example, adding sodium chloride to a solution of silver chloride reduces the solubility of silver chloride. The common ion effect is important in analytical chemistry and helps control precipitation reactions. Industries often manipulate equilibrium conditions to maximize product yields. By adjusting temperature, pressure, and concentrations, they can push reactions toward the desired products. For example, in the production of sulfuric acid, controlling equilibrium is critical for efficiency and profitability. These strategies are based on a deep understanding of equilibrium principles. Equilibrium concepts are also vital in environmental chemistry. Processes like the dissolution of gases in water, formation of acid rain, and pollutant removal all involve equilibrium reactions. Understanding these balances helps scientists develop strategies to protect the environment and manage pollution. Equilibrium is truly everywhere from the lab to the natural world. These tables, standing for initial change and equilibrium, are a helpful tool for solving equilibrium problems. They organize the concentrations of reactants and products at different stages of the reaction. By filling out an ICE table, chemists can systematically calculate unknown values and predict the outcome of a reaction. Mastering ICE tables is a must for anyone studying equilibrium. Reaction quotient Q is similar to the equilibrium constant but uses current concentrations instead of equilibrium concentrations. By comparing Q to K, chemists can predict which direction the reaction will shift to reach equilibrium. If Q is less than K, the reaction moves forward. If Q is greater, it moves in reverse. This comparison is a powerful way to analyze chemical systems. Gibbs free energy, symbolized as delta, is a measure of the spontaneity of a reaction. At equilibrium, delta is zero, meaning there is no net change in the system. The relationship between delta and the equilibrium constant K helps chemists understand whether a reaction will proceed spontaneously or require energy input. This connection is fundamental in thermodynamics and chemical engineering. Electrochemical cells, like batteries, also rely on equilibrium. The balance between oxidation and reduction reactions determines the voltage and efficiency of the cell. By understanding and manipulating these equilibria, scientists can design better batteries and fuel cells. Electrochemistry is a perfect example of equilibrium in action, powering many devices we use every day. Some equilibrium reactions are accompanied by color changes, making them easy to observe. For example, the reaction between iron Roman 3 ions and thiocyanate produces a red complex at equilibrium. Shifting the equilibrium by adding more reactant or product changes the color intensity. These visual cues help chemists monitor reactions and understand equilibrium shifts in real time. Gas phase reactions often reach equilibrium quickly and are sensitive to changes in pressure and temperature. Examples include the synthesis of ammonia and the formation of nitrogen oxides. Understanding how gases behave at equilibrium is crucial for designing efficient chemical reactors and controlling emissions in industry. While equilibrium tells us about the final balance of a reaction, reaction rates describe how quickly that balance is reached. Some reactions reach equilibrium in seconds, while others take hours or days. Factors like temperature, concentration, and catalysts affect both the rate and the position of equilibrium. Understanding both concepts is essential for controlling chemical processes. Let's look at some examples of how equilibrium can be disturbed. Adding more reactant, removing a product, changing the temperature, or altering the pressure can all shift the equilibrium position. Each change prompts the system to respond in a way that restores balance, as predicted by Chatellier's principle. These examples help illustrate the practical applications of equilibrium concepts. Maintaining equilibrium is not just about efficiency, it's also about safety. Sudden shifts in equilibrium can lead to dangerous conditions, such as pressure buildup or unwanted byproducts. Industrial chemists carefully monitor and control equilibrium to prevent accidents and ensure safe operation of chemical plants. Safety is always a top priority in chemical engineering. Equilibrium isn't just for scientists, it's part of our daily lives. From carbonated drinks to the way our bodies process oxygen, equilibrium reactions are everywhere. Even cooking and cleaning involve chemical balances. Recognizing these everyday examples helps us appreciate the importance of equilibrium beyond the laboratory. While equilibrium concepts are powerful, they have limitations. Not all reactions reach equilibrium, especially if products are removed from the system or if the reaction is too slow. Some reactions go to completion, leaving no reactants behind. Understanding these limitations helps chemists choose the right approach for each situation. Energy changes play a big role in equilibrium. Exothermic reactions release energy while endothermic reactions absorb it. The balance between energy input and output influences the position of equilibrium. By understanding these energy changes, chemists can design reactions that are both efficient and sustainable. The pathway a reaction takes, known as its mechanism, can influence how quickly equilibrium is reached. Some reactions have multiple steps, each with its own equilibrium. Understanding these mechanisms helps chemists control reaction rates and yields, making processes more predictable and efficient. Analytical chemists use equilibrium concepts to detect and measure substances in samples. Techniques like titration, spectrophotometry, and chromatography all rely on equilibrium reactions. By understanding and controlling these balances, scientists can obtain accurate and reliable results in research and industry. Development and testing of new drugs often involve equilibrium studies. Understanding how drugs interact with biological molecules at equilibrium helps scientists design more effective and safer medications. Equilibrium concepts are also used in drug formulation and delivery, ensuring that medicines work as intended in the body. Food chemistry is full of equilibrium reactions. From the browning of bread to the fermentation of wine, these processes depend on chemical balances. Controlling equilibrium helps food scientists improve flavor, texture, and safety. Understanding these reactions also helps us appreciate the science behind our favorite foods. Water treatment plants use equilibrium principles to remove contaminants and purify drinking water. Processes like precipitation, adsorption, and ion exchange all rely on chemical balances. By controlling equilibrium, engineers ensure that water is safe and clean for communities. This is a vital application of chemistry in public health. The atmosphere is a giant laboratory where equilibrium reactions determine the levels of gases like carbon dioxide and ozone. These balances affect climate, air quality, and even human health. Understanding atmospheric equilibrium helps scientists predict weather patterns and develop strategies to combat pollution and climate change. Materials scientists use equilibrium concepts to develop new alloys, ceramics, and polymers. By understanding how atoms and molecules arrange themselves at equilibrium, they can design materials with specific properties. This knowledge is essential for creating everything from stronger metals to flexible plastics. Renewable energy technologies like fuel cells and solar panels rely on equilibrium reactions to generate power. By optimizing these reactions, engineers can improve efficiency and sustainability. Equilibrium studies are driving advances in clean energy, helping us transition to a greener future. Art conservators use equilibrium principles to preserve paintings, sculptures, and historical artifacts. Chemical reactions can cause deterioration, but by controlling equilibrium, conservators can slow or even reverse damage. This intersection of chemistry and art helps protect our cultural heritage for future generations. Forensic scientists use equilibrium reactions to analyze evidence from crime scenes. Techniques like drug testing, toxicology, and DNA analysis all rely on chemical balances. By understanding equilibrium, forensic experts can provide accurate and reliable results in criminal investigations. Agriculture relies on chemical equilibrium for soil fertility, crop protection, and fertilizer production. Understanding how nutrients and chemicals interact at equilibrium helps farmers optimize yields and protect the environment. Equilibrium studies are essential for sustainable agriculture and food security. Nanotechnology involves manipulating matter at the atomic and molecular scale, where equilibrium plays a crucial role. By controlling chemical balances, scientists can create nanoparticles with unique properties for medicine, electronics, and energy. Equilibrium is at the heart of many breakthroughs in nanoscience. Space missions rely on equilibrium reactions for life support, fuel generation, and waste recycling. Understanding how chemical balances work in microgravity helps engineers design systems that keep astronauts safe and healthy. Equilibrium studies are paving the way for longer and more ambitious space journeys. Wrap up: chemical equilibrium is a fundamental concept that explains how reactions reach a balance between reactants and products. It's dynamic, influenced by various factors, and essential in countless fields, from industry and medicine to the environment and beyond. By understanding equilibrium, we gain powerful tools to control and optimize chemical processes, improve our daily lives, and solve global challenges. Thanks for joining this journey through the world of chemical equilibrium.